Okay, well, let's see. I have posted homework 5. Homework 5, last homework assignment, it'll be due 1 week from today. It covers clustering and the EM algorithm, which I will cover in today's lecture. I have posted, so if you were to take 102B during like spring or during the regular school year, there would be 6 homework assignments, and the last homework assignment would cover PCA, Principal Components Analysis. No homework for you. You don't have a homework 6, so that will not be there. But I have posted at least portions of homework 6 that are relevant for the final exam, because PCA will appear on the final exam, and so if you want the practice, you can kind of look at this homework, at least some of the homework prompts. Now, of course, the homework is different from the final, because the final, is pen and paper, and then the homework you do on the computer. But you can kind of make like a smaller version of the homework problem with just like a handful of observations or something, and see if you can kind of work through it yourself. But anyway, we have that. So that's homework 5. I guess I'll go ahead and talk about the final exam, and then next week, we have lecture on Monday, and I'm considering either just making Monday's lecture optional or canceling it, or just maybe just doing something, just because I don't like to lecture on a thing and then test you on it 2 days after, right? So I'll try to cram as much as I can into today's lecture, and then next week's Monday lecture, we'll just kind of keep it light, not get into any kind of heavy stuff, and then you'll have your final exam on 6th week Wednesday, because we don't have that. We don't have a separate finals week where you have some time. But anyway, okay, so let's go ahead and look at the final exam. This is document kind of covering this. This is, so again, it'll be in this classroom, seating chart. I'll probably just use the same seating chart. Was that okay? What the last seating chart? Okay. So you'll be allowed to have 2 full sheets of notes, front and back, handwriting or typed, and these are the problems. Okay, and then you'll have the full class time. It'll probably take you have an hour and 50 minutes in class time. I imagine it'll take maybe an hour and 20 to complete hour and a half. And then of course, if you want to take the full amount of time, you are allowed to do so. Okay, so you'll have a KNN classifier problem. I'll provide some training data, and there will be, the training data will be in 2 classes, and I'll have all of those points labeled, and I'll say, here's a test case, all right, and if K were equal to 3, how would this test case be classified, right? And here's if a test case is over here, and K were equal to 5 or 7, how would this be classified? And so you'll just kind of look, you don't actually have to do calculations, it will be on a grid, and I mean, you can kind of, I imagine you'll be able to count and determine how far away the points are. I suppose you could bring a compass and try to figure out, what, but I think it'll be simple enough, and I'm not gonna ask you to do your calculations and do 2 squared plus 5 squared is, a square root of that to get your Euclidean distance. You don't have to do that, okay? You can just kind of look at it. So that's that. There will be a support vector machines problem, and basically I will have, kind of a diagram of some of these things, and I will ask, I will say, I created these boundaries using either a linear or a Gaussian RBF kernel, and I have altered you know, the cost parameters, I've altered the gamma parameters, okay? And I will ask you which boundary corresponds to which set of parameters, right? So which one has a cost of, and these are just made up, but you know, this would be like linear boundary, okay? And we have a, you know, a point on the wrong side. So for linear, that means you got a low cost, whereas if you have a high cost for misclassification, this is supposed to be a straight line. This would be kind of your linear with a high cost. You know, when you have very kind of squiggly boundaries, that indicates a high gamma, whereas smoother boundaries indicates a lower gamma. You know, when you have misclassifications, that probably corresponds to a lower cost. And, you know, kind of depending on things. And it's a little ambiguous with these pictures. I think on the final exam where you see the diagrams, it should be, you know, more clear. You had kind of problems on this in homework 4, and if you kind of, you know, study those, or, you know, create your own little test sets with different classes, and, you know, just kind of play around with high gamma, low gamma, high cost, low cost, and see what kind of boundaries. I think you'll get a better sense of kind of the behavior of SVM, which, you know, the hope is, you know, in the future, when if you ever decide to use SVM as a classification method, you'll have a sense of, you know, do you want high variance or low variance, higher bias, lower bias type of situation in your application. So anyway, you'll have that. It's just going to be kind of pictures and matching, right? Which command ends up with which picture. You will have, I will have a k-means clustering problem where you will do the k-means clustering by hand. So I will provide some data in 2 dimensions. So, you know, it'll be a matrix with 2 columns. It'll probably be a fairly small data set, maybe 5 points, 6 points, something like that. Well, actually, I suppose, you know, maybe not too many points, maybe 8 points at most, okay? And I will have random initial assignments. So I'll say, okay, this point 1 is in cluster A, this is in cluster B, this is cluster A, cluster B, so on and so forth. And then I will ask you to do maybe 1 or 2 full iterations of k-means clustering. So starting off with those random assignments, you will then calculate, okay, what is the mean of all the points assigned to cluster A? What is the mean of all the points assigned to cluster B? Then you'll, you know, there will be a plot, so you can see them. You'll plot where the centroids are, and then based on that, you should be able to just visually assign points to the nearest centroid. If you're not sure, you can do calculations, but you're not required to. And then you'll kind of do that, and then, you know, once you reassign the points, you'll recalculate your means, your centroids, and, you know, redo assignments if I ask for 2 iterations. Okay, so, you know, just kind of be comfortable with the idea of doing k-means clustering kind of manually by hand, and that should, you know, hopefully that means you understand how the algorithm works. Okay. We'll also have a problem where you do k-means clustering with a kernel function. And this one, I will have you transform from 2D into 3D, and then you'll do k-means clustering using your 3-dimensional points. And I'll have, for this one, I'll have a very small kind of data set, and I will also provide the initial cluster assignments. And, you know, once the data is in 3D, it becomes a little bit more tedious to calculate distances and reassign points to centroids, so I won't ask you to do more than 1 iteration. If you can do 2 iterations up here, you can do 2 iterations down here, but I'm only going to ask you to do 1 just because it gets more tedious. But that will be k-means with a kernel function. Okay, a Bayes classifier problem. This one, I will provide some data, and they will be kind of labeled. And the data will come from either a binomial distribution or a normal distribution. So for an example of a binomial, or okay, here, I'll talk about just possible types of examples, okay? So you'll get, for a Bayes classifier, you need, to get your posterior probability, you need the likelihood, you need the prior probability, and then you'll need to calculate the marginal probability. So the likelihood will come from either a binomial distribution or a normal distribution. Probably in your note sheets, it's good to include what the PDF is of these things. And then, for the prior distribution, you'll just use your training data. So if the training data is 50% class A, 50% class B, that will be your prior. If your training data is 75% class A, 25% class B, that will be your prior probabilities, okay? And then I will give you a test case, and I will ask you to use the Bayes classifier. So for this test case, it'll just be, one kind of value, and I'll ask you to use the Bayes classifier to determine the probability that it's class A or class B, okay? So an example where the likelihood is a normal distribution, okay? So here is a data set where you have 5 people, and we have the heights of 5 people, and we'll say male 70 inches tall, male 73 inches tall, female 65, 62, 69 inches tall. And we're going to say a person is 68 inches tall. What is the Bayes classifier probability of the person? So based on our data, the mean height for males would be 71 and a half, and the mean height for females would be, 5 plus 2 plus 9, something, 68 is 67, I don't know, I can't, 7 plus 9 is 16, 16 divided by 3, 5, okay, 65.3, 65.7 inches, okay, something like that. So that would be the mean for female, and then, you calculate your standard deviation using your calculator or whatever. And then based on that, you would calculate with the normal PDF, right? You'd plug in 68 inches, and you do 68 minus the mean divided by your standard deviation. You put that into your PDF to get some value, your density function for male, density function for female to get your likelihoods, multiply it by the prior probability, and then, calculate that. Does that kind of make sense as far as calculating a posterior probability of whether a person who's 68 inches tall, what's the probability this person is male or female, depending on this training data? Obviously, this training data is very limited, not going to be easy. Okay. On the other hand, a binomial example. This would be a lot like the example in the lecture notes where I have, a bag with marbles or something. Probably it's not going to be bags and marbles, but some kind of thing where the thing gets filled, and it's either going to be, some proportion blue, some proportion something, okay? And we'll say, factory A produces 10% blue, factory B is 20% blue, factory C is 30% blue, and here you get a bag with 20 pieces and 3 are blue, so your bag is 15% blue, and, which factory do you think it came from, okay? And the prior probabilities are 10 came from factory A, 5 from factory B, 5 from factory C or something, okay? And you'd use Bayes classifier there. EM algorithm. EM algorithm is used for, is an unsupervised learning problem, and we will cover it in today's lecture. But I will, so in today's lecture, EM algorithm, we're going to look at 2-dimensional data. But for the exam, I will give you 1-dimensional data, unidimensional data, and I will tell you that the distribution that produced the data is the normal distribution, and the EM algorithm is iterative, and so basically you will have kind of your current estimates of what your mean and standard deviation are, and using that, you will redo your kind of classification probabilities for the EM algorithm. And so I will ask you to recalculate the weights and recalculate your weighted means. I think this prompt will make more sense once I cover what how the EM algorithm works today. Okay, and then similarly, there will also be PCA on the final exam, and I will provide you a small matrix in 2 dimensions, and you will try to do some dimension reduction to reduce it down to 1 dimension. And you will find the first principal component. So to do PCA, part of it is you will need to find the eigenvalues and eigenvectors of a 2 by 2 matrix. Okay, so that's part of the step of doing principal components analysis. So if it's been a while since your linear algebra class, you might need to brush up, or certainly you should brush up on how to calculate or how to find eigenvalues and eigenvectors of a 2 by 2 matrix. Okay, it's a lot harder to do it for like a 3 by 3 matrix or higher dimensional matrix, but I think it is reasonable for me to ask you, well, it is reasonable to ask you to calculate eigenvalues and eigenvectors for a 2 by 2 matrix, which is what I will ask you to do. Or I won't specifically ask you to do that, but that's a necessary step for PCA, and so and you'll take the first principal component and do PCA analysis to reduce from 2 dimensions down to 1 dimension. Okay, and then the last page will be a handful of kind of conceptual questions that span the entire course. So pretty much almost all of the final exam is everything after the midterm exam, with the exception of some conceptual stuff. So no kind of calculations, no punching in numbers, but there might be some conceptual topics spanning the entire course. So something like, I don't know, which, would you use lasso or ridge regression, as far as regularization goes, would you use lasso, ridge, or both for variable selection? And your answer would be lasso, because lasso can reduce coefficients down to 0, whereas ridge regression doesn't actually reduce them down to 0. It shrinks them, but it doesn't reduce them down to 0. Stuff like that, okay? So kind of conceptual topics there. Okay, any questions on what would be expected for the final exam? Okay, and then, just like everything else, like, don't look up past final exams. You can put pretty much anything on your note sheet. You can't look up past final exams, and you can't like take problems from past final exams and put that on your note sheet. But for your note sheets, if you want to take examples from the homework, shrink them down and put them on there. If you want to take lecture slides, shrink them down and put them on there, that's fine. If you want to handwrite everything, also fine. So that's fine. I didn't study all of your note sheets from the midterm exam very, very thoroughly, but just kind of quickly glancing, I didn't see any problems with that. Okay. And that's 1 week from today. It's hard to believe that our class is over, or pretty much. I got one more lecture to give you, but that's that. Okay, let me give you your first view quiz answer for today, which is the letter B. B is your first view quiz answer for today. Okay, week 5. Oh, what happened? Okay, something. I don't have. The file hasn't synchronized yet. And then the PCA lecture for today, I'm just taking the one from spring quarter. I'm just taking that, the lecture from spring quarter, which came out in week 9. So all of these dates are all messed up. I think we can get through both of them today. Okay, let's take a look at the EM algorithm. Okay, EM algorithm is expectation maximization algorithm. We use it in situations where we have both missing data, or missing data and unknown parameters. And then here's there's a short little video from Ritvic Math that covers this, UCLA alum. But conceptually, and so this example comes, I'm borrowing it from Ritvic Math's example. But let's say you are told you have these values, 1, 2, and x being unknown, and you say this is drawn from a normal distribution, and the normal distribution has a mean of 1 and a standard deviation of 1, okay? So in this case, you have a missing value, but your parameters for the distribution that generates your data is known. And so if we ask, hey, what is this missing value of x? Well, you don't know. It's a random value coming from the normal distribution, so you don't really know what that value x is. But if you had to say, what is your best guess? What do you think is the most probable value for x? You would say, okay, well, let's look at our normal distribution. The point with the highest density, so basically your highest likelihood value, is going to be 1, right? So if your normal distribution has mean 1, of course, the random value that comes out could be any value, technically from -infinity to +infinity, but high probability that it's between that it's close to 1, okay, and 68% between 0 and 2, and 95% between -1 and +3, and you're kind of the best guess for the what x is would be 1. So that's what you have if you have missing values. Okay, over here we're going to say we have known values 1, 2, and 0. And we're going to say they are drawn from some distribution, but this distribution, the mean is unknown, standard deviation is 1. So what do you do here? You use maximum likelihood estimation. You say, okay, well, my data values are 1, 2, and 0. What is the mean of this distribution? Okay. Again, the mean of the distribution could really be any value, but the value for mu that's going to have the highest likelihood is going to be the mean that is basically at the center of your sample of values, okay? And you'd say, okay, well, what's the likelihood of this? And basically you take the mean of 0, 1, and 2, and the mean of 0, 1, and 2 is 1, and so you'd say the value of mu that maximizes the likelihood of my data is going to be mu equal to 1. Okay, but again, in all of these cases, the mean could be something a little bit different, right? So these are, I think we're familiar with both of these kinds of scenarios. Okay. What if we are in this situation, though, where we have data, 1, 2, and a value is unknown, and we say this data comes from a distribution where the mean itself, mu, is unknown. And so now my question is, what is your best guess for what x is and what the unknown parameter mu would be? Okay. And so how do we approach this? Well, I mean, this is simple enough where you might be able to just jump at the answer. But we could take an iterative approach, right? And we could just say, all right, well, let's just take a guess, an arbitrary guess for what x could be. And we're going to say, well, what if we set x is 0, okay? And if x is 0, then what would my guess for mu be, all right? And if we do that, then my data would be 1, 2, 0, and based on that, my best guess for mu would be 1. Now, if my guess for mu is 1, then I should go back and update what I think my missing value is. And so if I'm guessing my mu is 1, this is going to become 1, 2, 1, right? And if I update this to be 1, 2, 1, then I should update what my guess for mu is. And if I do that, 1, 2, 1, you do 4 divided by 3. My guess for what mu is going to be 1.33. okay? And I would update my guess for mu. And then I go back and I get 1, 2, 1.33, and I kind of do this iterative approach. I go back and forth and I say, okay, let's update what my guess for x would be, or what is kind of the most probable value for x. And then once I estimate what my most probable value for x is, I'm going to go back and I'm going to update what my guess for what mu is. And I do this iterative back and forth, and eventually we iterate kind of back and forth, and we'll converge to x. Best guess for x is 1.5, and the best guess for mu is going to be 1.5. Okay, does that kind of conceptually make sense as far as what we're doing in this kind of iterative approach? Okay, and that's basically the EM algorithm. Is we take this iterative approach where we're going to try to update what my guesses are for the missing values, and we're going to update what my estimates for these parameters are. And so kind of you could apply the EM algorithm for a bunch of different kinds of applications, but perhaps you know, a nice application and you know, one that's, you know, satisfying and, you know, visually good is we can apply the EM algorithm for a mixture of normal distributions, Gaussian mixtures. And so the idea here is the data we have is going to be a mixture of 3 multivariate normal distributions. So this is going to be our data generating process, and we're going to have data you know, kind of coming from these 3 different classes. But again, the EM algorithm is unsupervised, right? It's unsupervised, meaning the data come in unlabeled, and we don't know, we're going to search for the internal structure in this unlabeled data. We don't have the answers off the bat. Okay, so unsupervised learning are things like clustering, where the data comes in unlabeled and you're searching for kind of groups or clusters. Here, same thing with the EM algorithm. Our data comes in, but which cluster they belong to is unknown. That's kind of our missing values. The other part that's also missing is, well, we don't know what these clusters are, and we don't know what the mean of this cluster is, and we don't know the standard deviation of these clusters. Here, because I'm generating the data, I know the answers. I can say one component is going to come from, have a mean of 0, 0, and the sigma matrix, if this is a multivariate Gaussian in 2 dimensions, sigma matrix is going to be 9, 0, 0, 9, meaning we have variance of 3, standard deviation of 3 in each direction, or variance of 9 in each direction, and there's no covariance. So basically, because you have the same variance in each direction, it's going to look like a big circle. Here, a second component is centered up at 4, 4, and the variance is, you know, 1. It's down the diagonal, and the off-diagonal elements is 0.9. So we have high covariance between x1 and x2. And then component 3, it's centered at -4, -4, and you have negative covariance, okay? Variance of 2 and covariance of -1 here. They are generated with a mixing proportion of 0.5, 0.3, and 0.2. So component 1 is going to account for 50% of the data, component 2 will be 30% of the data, and component 3 will be 20% of the data. So if these are our mixing components, what is the overall PDF of the values that we have? The overall PDF is going to be basically the sum of our mixing proportion, our alpha value, which is either 0.5, 0.3, or 0.2, our mixing proportion multiplied by the PDF of each component distribution. Okay, so the overall mixture of this 2-dimensional Gaussian for each, the probability of getting some value x given your parameters, so x is the point in 2-dimensional space, and then this fat theta right here is basically just all the parameters, all the all the parameters, which is the combination of all the mu's, all the sigmas, and the alphas, okay? So this is just to say all the parameters, so all the means, all the standard deviations, all the sigmas here, is going to be equal to the mixture component. So is 50% comes from component 1, 30% from component 2, 20% from component 3, multiplied by the PDF, okay? PDF which is your multivariate distribution. And here the given components here are z sub k. Z sub k is the indicator variable on whether the point belongs to cluster K or not, or component K or not, okay? And then theta sub k is the combination of basically your mu and sigma parameters. So theta kind of gathers all the parameters. Z is the indicator variable on whether a point belongs to a component or not. And so we multiply all of these things and we add them up for all of the components. So you're going to get, the PDF for cluster 1 plus the PDF for cluster 2 plus the PDF for cluster 3, all kind of multiplied by alpha. And because alpha itself sums up to 1, and we know the PDFs themselves integrate to 1, we also know that the entire kind of mixture will integrate to 1 as well, the product of these things. This is kind of a lot of notation here. I think it'll just make a little bit more sense once I kind of plot it. Okay, but this is how I'm going to generate our data. I got my mixing proportions in this vector alpha 0.5, 0.3, 0.2. I have my vector for the mean of component 1. I have my matrix for the variance and covariance of component 1. Same for component 2, component 3. I gather the means up in a list. I gather the variance matrices in a list as well. And I'm going to generate my data this way. I say, all right, we're going to start off with an empty matrix, or I guess a matrix of zeros with 1,000 rows and 3 columns. And for each row, I'm going to draw a sample of value, and I'm going to say, give me either a random 1, a 2, or a 3, right? And the probabilities of getting 1, 2, or 3 are determined by alpha. So it's going to generate the number 1 50% of the time, the number 2 30% of the time, the number 3 20% of the time. And then once I have which component it belongs to, I'm going to ask the multivariate normal, give me a random multivariate normal value. So it's going to generate a point in 2 dimensions. And I ask for just one at a time, where the mean is either the mean of component, if k is 1, it's going to be the mean of component 1, sigma component 1, okay? And then we're also going to, so the 3 columns here is basically our x1 component, our x2 component, and which cluster it came from, or which class it came from. So RMV norm is going to generate a point in 2 dimensions, and then it's going to also record what value of k is. And so we do this 1,000 times, and I ask, go ahead and plot this, okay? And so here's our data. We have 50% of the data coming from a cluster centered at 0, 0, with variance 3, or variance 9, or standard deviation 3 in each direction. We have 30% of the data coming from a cluster centered at 4, 4, with high covariance. And then 20% of the data, and you might not have an easy time seeing this, but 20% of the data comes from a cluster centered at -4, -4, with some negative covariance between x1 and x2. Okay, so this is how the data comes in. The data is completely unlabeled. This is an unsupervised learning problem. And we're going to ask the EM algorithm, can you identify clusters? Can you identify clusters in this unlabeled data? Now, because we generated the data, we know the answers. Okay, we know here's the labeled data, that these points, centered at 4, 4 with high covariance, centered at -4, -4 with negative covariance, and then a lot of points centered at 0, 0. Okay, but because it's random, this one centered at 0, 0 produces points, all the way out in these different directions here. Okay. All right. So this is how our data comes in. Again, it comes in unlabeled. And there's kind of a question. All right, what about this point right here? How should we assign this to a cluster? Does it belong to this cluster up here? Does it belong to the center cluster? How do we assign a point to a cluster? And this is where the EM algorithm really kind of differentiates itself from k-means clustering. So k-means clustering and EM algorithm are similar, okay, except in that they're both iterative, right? K-means clustering, you start off with some points, you calculate the centroids. Once you calculate the centroids, you reassign points, recalculate centroids, reassign points. EM algorithm, we're going to be doing something similar. We're going to calculate means and variances. We're going to reassign points, means and variance, reassign points. The difference here, though, with the EM algorithm is rather than saying this point belongs to, this cluster over here, cluster 1 or cluster 2, we do a probabilistic assignment. We say this point right here could come from cluster 1, or it could come from cluster 2. I would give it 50% cluster 1, 49% cluster 2, and 1% cluster 3, or something like that. We're going to do a probabilistic assignment of points rather than a direct assignment. K-means clustering says this is the nearest centroid, therefore it belongs to this cluster. EM algorithm is going to do probabilistic assignments. It's going to say based on this value and the properties of the clusters that we have, we're going to say it's 50% cluster 1, 49% cluster 2, 1% cluster 3. Okay, so we are going to handle this probabilistically. So I wrote, rather than strictly assigning a point to one cluster like we do in k-means clustering, what we are going to do is we're going to do a probabilistic assignment, and we do that using the Bayes classifier. So hopefully we remember the Bayes classifier, and when we do that, we get a membership weight, right? So you did your homework, you did Bayes classifier, you said this point, I guess you did naive Bayes classifier, but same idea, okay? You say, okay, based on this, petal length and what is it, petal length, petal width, or whatever, it's 89%, setosa or something like that, okay? But it's 10% versicolor or something, okay? We get membership weights for each of these points, and then what we will do now is when we calculate, so in k-means clustering, you got your points, and then you calculated your centroid of the points that belong to that cluster. Here, you're going to get probabilistic assignments, probabilistic membership weights for every single point, and we're going to calculate a weighted mean. We're going to say this point is like 99% belongs to cluster 1, so it's going to contribute 99% towards the mean of cluster 1. This other point is only 20% probability cluster 1. So when we calculate the mean of cluster 1, we're going to put 99% on this value, 20% on this value, and we're going to calculate the mean that way. So we get a weighted mean, right? So we're going to get a weighted mean for the center of this cluster. We do the same thing for the variance matrix. We're going to get the weighted mean of not the weighted mean, but the weighted version of the variance covariance matrix. And by using kind of these weighted versions of the mean and the variance covariance matrix, this maximizes the likelihood of the values that are, quote, assigned to each cluster. And then we iterate back and forth. So we get kind of our weighted means and variance clusters. And then once we have that, we go back and we iterate and we say, all right, now that I have updated means and variance values, what is the probabilistic assignment? This point belongs to each of these clusters. And so you can think of the EM algorithm as a blend between k-means clustering and the Bayes classifier. So if you understand k-means clustering and this iterative reassign, recalculate, but you also understand the Bayes classifier that says we're going to get probabilistic values for each kind of class. The EM algorithm is a bit of a blend of that. We are going to reassign and recalculate, but the recalculation is done using the Bayes classifier, and the reassignment is done using the Bayes classifier, and the recalculations are done using weighted versions of the mean and covariance. So the Bayes classifier comes in on our E step, which is how we get our membership weights. Okay, and we're going to say, the probability that some point belongs to this particular cluster. Okay, so the weight that observation I belongs to cluster K is going to be basically our likelihood times the prior divided by the marginal. The likelihood is you plug in the value of that coordinate into basically, the PDF for each of the different clusters. So you say, okay, what is the likelihood that this observation comes from this cluster with this mean and variance? What is the likelihood that this observation comes from the cluster with this mean and variance? And what's the likelihood that this observation comes from the cluster with this mean and variance? We're going to multiply that by the prior probabilities alpha, and then we do this for all of the different classes. We sum that up to give us our marginal so that these things add up to 1. Okay. Now, this alpha, the alpha is kind of our prior probabilities, which is kind of like how many points are assigned to each cluster. So if we have 1,000 points and 600 of them are assigned to cluster 1, our prior probability would be 0.6 for cluster 1. And if 300 are assigned to cluster 2, then our prior probability is 300 over 1,000, 0.3. Okay, but the thing again is we don't have direct cluster assignments. We don't say this point belongs to cluster 1 and this point belongs to cluster 2. So the quote number of points assigned to each cluster is actually just the sum of the weights. Okay, so this point is 99% cluster 1, and so it's going to, how many points are assigned to cluster 1 so far is 0.99. Okay, maybe we have another point that's 30% cluster 1, and we add those together. So far we have 0.99 plus 0.3, 1.29 points are assigned to cluster 1. And we do that for all of these things. So it's not exactly the number of points. It's not going to be an integer value. It's going to be the sum of all of the membership weights for cluster 1 and the sum of all the membership weights for cluster 2. So you're going to get some, you can think of this as an analog for the number of points assigned to cluster K, but it's not an integer. It is the sum of the weights. It's going to be, whatever floating point value we have here, some real number and some decimal value. Okay. Does that kind of make sense for the membership weights? And so we do that. We have the density function here, and again, the PDF for the multivariate normal is this kind of complex function, or complicated function. I shouldn't say complex. We're not dealing with imaginary numbers here. We are going to just use DMV norm from R. So R can calculate the density of the multivariate normal. We're going to plug in the observation that we are looking at, and we'll put in our current estimate of the mean of cluster K and the variance of cluster K, whatever those values are at this moment in time. And we get our likelihood values. So we get our likelihood, and we get our prior. We calculate that for all of the different clusters, and we get our marginal probability that way. Okay, so you do that for all of the points. You calculate the membership weights of all the points to each cluster, and then what we have to do now is we recalculate basically the centroid, or the mean, of each cluster. And so to do that, we're just going to take the weighted mean of all the points of all of our x values. Okay, so our weights here could really be any value from 0 to 1. And basically, if the only difference here, if you think about how do we calculate the centroids in k-means clustering? We had a vector z, and a vector z was either 0 or 1. The point belonged to cluster K or it didn't. And here, w is a real number between 0 and 1, where probably a lot of your values might be like 99% or 1%, but maybe even like 50% or something, right? Depending on what the Bayes classifier says. And so we multiply those membership weights times x, we sum them up, and we divide by n sub k being our sum of the weights. And so that will just be the weighted mean of all the points for each of the clusters. Okay, so you have different weights for cluster 1, different weights for cluster 2, different weights for cluster 3, and you get a weighted mean for all of these clusters. Similarly, to calculate your variance, we're going to have a weighted variance. So if I just got rid of this thing, we would just have the variance. The variance covariance is x minus mu times x minus mu transpose divided by 1 over n. I guess the unbiased version is 1 over n minus 1, but here we're going to just use the weighted version. And so we're going to weight each of these products using w sub ik, and then we divide by n sub k again being the sum of the w's. So we get a weighted version of the variance covariance matrix for each cluster. So you're going to get it for cluster 1, cluster 2, and cluster 3. Okay, and that's pretty much it. That's how the EM algorithm works. I will illustrate what this looks like iteratively. So again, our data come in completely unlabeled, and we are going to ask the EM algorithm, try to identify 3 clusters. Try to identify 3 clusters. See, these are the true labels. The labels, here I have red, black, and green, or I think the order in R is black, red, then green. But the labels are arbitrary, okay? So I'm going to start off with just some terrible initial values. I'm going to say our mixing proportions are 0.33, 0.33, and 0.34. So pretty much even mixing proportions. My initial values are going to be 0, -9, -9, and 9. And so we're going to start off with a mean here, a mean here, and a mean here. And we're going to ask it to try to identify the 3 clusters. One thing to note, when I color these in, okay, the points get colored in as either green or black or red. Now, this is a little bit of a lie in that, these points right on the border are probably 51% green, 49% black. And these points over here are 51% black, 49% green. And that's how the Bayes classifier would classify these points. You get probabilistic assignments. However, when I plot them, I'm not able to color a point, 51% green, 49% black, or something like that, okay? I mean, I guess there's like a gradient thing, but I think our eyes would have a really hard time distinguishing these different colors if I tried to do that. So here I just said take whichever cluster has the highest probability. If it's 51%, take that color and color it, okay? So these points are getting colored green, but they're not actually green. They are probably 51% green, okay? And these points are getting colored as black, but they're not really belong to cluster black. They are probably 51% black, 49% green, something like that, okay? But this is just what it looks like. But I'm going to go ahead and we're going to do this. And basically, we're going to say, okay, what is the weighted mean of all the points, okay? And so it's not just the points that are assigned to green. There's no assigned to green. It's like we do the weighted mean where these ones are like 51% green and 49% green and 30% green and 10% green and so on and so forth. We're going to get the weighted mean of everything green, weighted mean for black, weighted mean for red. We get the weighted variance and things like that. And so at the next iteration, oh, okay, so this is what I wrote, 49% red, 51% black. Okay, at the next iteration, this is where the means end up. Okay, so here's our mean, and then basically we also redo the variance, and so previously it was here, but after taking into account all of the data points, our updated variance matrix looks like this. So that's one iteration. Next iteration, we get something that looks like this. Again, we recalculate kind of all of our membership weights, and we recalculate the mean and the variance, and this is what we get. And I can just kind of keep running these iterations, and eventually this is kind of where it converges after each of these iterations. We get a mean over here, a mean over here. Your variance covariance kind of points this out, variance covariance points this out, and we have that, which is very similar to, so here's our final clusters. Here were the original clusters, or the true groups. Again, what gets labeled black or red or green is arbitrary, so it doesn't, so it's fine that it's different. What you see is that according to this, kind of the most probable things over here is everything is green, and the most probable thing for everything down here is red. But in reality, the points down here is a mixture of points coming from the center cluster and points coming from this lower cluster. And here we have a mixture of points coming from this cluster and points coming from the center cluster. But according to the EM algorithm, which just kind of says, all right, what's the probable thing that says, most probable is that all of these points up here come from this cluster and all of these points come from this cluster down here. Okay, and so that's the EM algorithm. Here's kind of if I just started off with different some bad starting locations. Okay, if I say, all right, let's start off over here and here and here. At the next iteration, we get this, and after a bunch of iterations, we end up getting, something. Okay, but basically, if you start off with like really bad kind of locations, you can let it run for a long time, and it might not converge to like the correct location here. So I have a whole bunch of slides, and you can just kind of slide through this thing, and you can kind of see how it updates. And I guess I wrote fast forward to the end, but I actually didn't have it fast forward to the end. But you can kind of watch these things kind of animate, which is kind of fun. but that's the EM algorithm. There's a similar animation if you look up EM algorithm on Wikipedia. There's some similar animation happening over here. So it has, this is old faithful eruption data where you have two input variables, the duration of the eruption, so this geyser, and you can measure how many seconds or how many minutes did this eruption last, and what was the length of time between different eruptions. And if you say search for clusters, it identifies these kinds of clusters. The initial thing starts off with kind of these bad parameter estimates where the center is up there and there, but again, after you reassign it, it kind of converges to these different things. Okay, the algorithm as described here is a little bit more, the notation's a little bit messier, but my hope is that these lecture slides kind of give you a sense of how the EM algorithm works, and you'll do it in your homework this week for homework 5. Okay, let me give you your second view quiz answer, which is the letter E. E as in elephant. E as in elephant is your second view quiz answer. Okay, and last topic is going to be PCA, Principal Components Analysis, and that will cover our course. I hope you've, despite, I know the quick pacing and the, the nonstop homework coming every single week, I hope you still enjoyed the class and found the content and material interesting. And I think is like instructor evaluations or course evaluations, is that a thing yet? Okay. I greatly appreciate you leaving, your comments and your evaluations there. That it always plays a role in our, our like promotions and our merit reviews and things like that. Because I actually don't do any research. I just teach only. So anyway, please leave a review there. Hope you enjoyed the class. Okay, so last topic, we'll cover Principal Components Analysis, PCA. So PCA also falls under unsupervised learning. So for unsupervised learning, kind of the big topics are clustering, and so we saw some clustering methods. We saw k-means clustering with the kernel function, and we just saw the EM algorithm, and those are all kind of clustering algorithms. And the other kind of thing that we look at in unsupervised learning is dimension reduction, of which Principal Components Analysis falls into this. Principal Components Analysis can also be used in, say, as a pre-processing step when you do like something like linear regression. Because when you do linear regression, we run into problems when variables have high correlation. So Principal Components Analysis basically gives us uncorrelated variables. And so the kind of the idea here is we're looking at dimension reduction. We have variables in our data set. A lot of them are correlated, and PCA basically transforms them into uncorrelated variables. The goal here is often dimension reduction. We can say rather than having a whole bunch of variables that have high correlations, can we just kind of reduce the number of variables that we're looking at? So an example is, I don't know if you've ever searched for an apartment or a house or something. Probably not a house, but when you go apartment hunting, there's things to consider, and one is going to be like, how big is the apartment, right? 1 bedroom, 2 bedrooms, 3 bedrooms, or something like that. How many square feet is the apartment? And in general, bigger apartments will have more bedrooms, more bathrooms, stuff like that. But there's also other aspects that you're looking at, like where's the neighborhood, where is it located, how close is it to my place of work or school or things like that. And then other things are like, how nice is the apartment? Is it like disgusting and falling apart? Is it nice, does it look nice? Does it feel clean and things like that? And I would say, a lot of these things can kind of, your rating of an apartment can kind of be boiled down to, I would say, 3 aspects. One being the size, one being location, and one being kind of like how nice it is. And if you kind of boil your apartments down to kind of these 3 things, that's going to sum up a lot of what you're kind of looking for. So rather than having to look at every single individual thing and say, okay, this is how many bathrooms and how many bedrooms and how many square feet it is, and this is we're going to look at this the median income of the neighborhood is this, and the crime rate of the neighborhood is this, and the local school rating is this, or things like that. You can kind of just boil it down to things. Scale, size, I give it a rating from 0 to 5 stars. Amenities or the quality, the niceness, we're going to give it a rating from 0 to 5 stars or something. Neighborhood desirability, rating from 0 to 5 stars or something like that, right? And then you can also think of this as like in some kind of game, you might have a character creation thing, and you have different aspects of the character's personality. Obviously, a person is much more complicated than just maybe like 5 aspects or something, but you can kind of boil, as far as the game is concerned, you boil down an entire personality or persona down to kind of these 5 little aspects. We're also familiar with other examples of dimension reduction. So, the one that's, the reason why dimension reduction is so helpful and desirable is that it's easier to compare things when there's only one thing to compare, okay? So your GPA, for better or worse, is this dimension reduction tool, right? We can look at your entire transcript, and there's all of these different things. This is the course you took, and this is the grade you got, and all of these things. Your GPA gives you just one number that kind of summarizes everything, right? And in college you just average everything out. But in high school, I think your GPA was weighted, right? And it's like if you took the harder class, it was like out of 5 points, and the regular class was out of 4 points or something. I don't know, that's how it was when I went to high school. I think it's still that way. And then so, I don't know about you, but was there like gamesmanship where you're like, okay, I don't want to take driver's ed, or I don't know, was driver's ed even offered at your high school or something? No? Okay. Well, so there was a thing where you were required to do like driver's ed or health or something, but this was like a 4.0 class, but everybody had to take it. And so those of us who wanted to like maximize our GPAs, we would look for ways to like take, say, like health, not at the high school, so we don't get a 4 to like bring our weighted GPA down, and something like that, because like a 4 was like getting a B in your honors class or something. So it's just like you end up getting these weird side effects when you realize, like, when everything gets dimension reduced, you lose that kind of nuance. And so there's like gamesmanship, right? And that's kind of what happens. I don't know, there's like college rankings, right? And we're like, oh, UCLA #1 public school and things like that, and we're very proud of this. But there's been scandals with like different universities trying to game their ranking in the schools by like what do they do? They hire these professors that would have like certain things, and they try to just increase their rankings, because again, we've reduced something as complex as the university experience, which has all sorts of different aspects, right? There's not just the academic, but the social and the quality of life in the neighborhood and all of that stuff, and it just gets reduced to this one thing where it's like, Harvard and Princeton are here, and I don't know, stuff like that, right? And it's so dimension reduction is useful, but it's also like, by definition, it's reductive. Okay, your SAT scores, which I guess is optional now, but I think a lot of people still take SAT exams. It tries to boil something as complicated as intelligence or whatever down to like maybe 2 numbers, a math reasoning and a verbal reasoning. There's no longer a writing thing, right? Or is there?
There's like an optional essay, but you don't like have to take the whole essay.
Okay. Well, anyway, so that's like a thing. And so you get these 2 numbers, but also dimension reduction can also be done even further, where you just add the 2 numbers and you get this 1 number, and we go, oh, you got a 1510, and we go, ooh, great, and it's like, whatever, right? Other things, like even in sports, so if, in the NFL, they evaluate a quarterback's performance using something called the passer rating, and that takes into account all kinds of stuff, like how many pass attempts and how many pass completions and how many interceptions and things like that. And it's like, the overall rating for this quarterback for this game, gets this 1 number. And we say this player had a better performance or worse performance. In the Olympic track and field events, you have like the decathlon or the heptathlon, and it's like you're competing in all of these different things, but on the podium, there's only 1 gold medal, right? And so you have to take, how do you combine all of these different scores, right? This person did really well in the the hurdles, but poorly when they whatever shot put, or I don't know how how this stuff works, right? But it's like, you know, there's like throwing parts and running parts and jumping parts, and like how do you combine that? And so these are all kind of dimension reduction things, and those are all different aspects. How, you know, one kind of way to do this, we can do dimension reduction is PCA. Okay, a visual representation of PCA is you can think of an object that casts a shadow. And so my apologies to those watching the video, but I'm going to come over here, and you know, my hand exists in 3 dimensions, and if I put it in front of the screen, you see my shadow here. And if you see this shadow, it's very clear that this is a hand, okay? But if I rotate my hand, you know, in something like this, it becomes a little bit less clear, you know, what object this is, right? Depending on, you know, if you see this and you see this shadow, you go, okay, that's very clearly kind of like a marker. You could probably even identify that this is a dry erase marker based on the shadow. But then if I have the rotation of the object to be something like this, now you're not so sure what it is. Is this a lipstick? Is this a flashlight? What is this, right? It's very difficult to kind of tell depending on how I rotated this 3-dimensional object and the 2-dimensional shadow it casts. So the idea of PCA is you want to, dimension reduction is basically rotating a higher dimensional object in whatever space, you know, and here I'm rotating it in 3D, and it's being reduced down to 2D. So, you know, we encounter this in real life, going from 3D objects down to 2-dimensional shadows, and there's kind of this, an analog, you could imagine, you know, 4-dimensional objects in hyperspace casting down 2-dimensional shadows. It's a very kind of a weird thing, but what we are hoping for is we're hoping to find a lower dimensional projection of our high dimensional data that at least resembles the original data. Okay. There is another website. This is called Explain Visually, and we're going to do PCA. And the website is setosa.io, based off of the IRIS dataset. Okay, so this is the website, setosa.io/ev/principal components analysis. Here is data that exists in 2 dimensions, and when you plot it, the x and y have high correlation between x and y. And PCA here is finding a rotation of the data, and so we are basically going to just change the axes to be this red and green, okay? And so we're just rotating, okay? And it's very easy to see that we are just rotating the data into this, and when we do this, now we see, is there covariance between principal component 1 and principal component 2? There's not. There's no kind of covariance between PC1 and PC2. They are orthogonal to each other. Whereas we don't, if we completely threw away the second principal component, okay, and we basically kept the data in PC1, so we have our 5 data points and it's spread out like this, I would argue we are not losing very much information, okay? If we need to sort them in order of y, we could do it. If we needed to sort them in order of x, we could do that, okay? And throwing away the second principal component, throwing away the second principal component here, by losing that, you know, we lose a little bit of information, but not very much. Now, things change, so that this works out well because you have highly correlated data. If you have, you can actually move these things around, okay? So if you have something like this is still a rotation of the original data. Now, we do lose a little bit of you know, some nuance here. Okay, so technically this observation right here has a larger y value than this observation over here. After the rotation though, or you know, this one ends up being the most extreme, and this one, this is kind of the second highest value. And so, you know, we do lose a little bit of kind of the nuance if we just reduce it down to one principal component. We lose the information in the second principal component. But all we're doing is, again, we're just finding a rotation of the data. If I changed this and you know, put our data kind of like this, the principal component analysis gets the axes, you know, would realign, and this is still just a rotation of the original data. Okay, so PCA is just a rotation, and we're just looking at basically what is the shadow if I, you know, cast a light starting from up here at the top and I cast them down, the shadow that these 5 data points produce in the first principal component direction is this. If I cast a light from over here, you know, what is the shadow that these data points produce on PC2? That's the these are the shadows that we get. Okay, so that's what we have. Here it is in 3-dimensional data. We have this rotating thing. We see there's kind of 3 clusters here. And right now, if we just have it exist in X, Y, and Z in our red, blue, and green axes, the original data, we don't really identify any of the clusters in X, Y, and Z. Okay, we see, okay, there's, you know, in X it looks like this, and in Y it looks like that, or something. Whereas if I do the principal components analysis, it's going to rotate the data. It's going to find some rotation of our axes here. Okay, and so I'm going to go ahead and click this, and it rotates the data in terms of the axes, and we see that if we look at just principal component 1 and we cast the shadow here, we see we do identify that there are kind of 3 clusters that exist in the original data. So despite the original data in X, Y, and Z, as it appears, it's hard to identify 3 different clusters looking at X, Y, and Z, and you really only see 3 different clusters when you have the 3D data here, right? So, you know, if I reset this, you know, if we're just kind of plotting X and Y here, it's you know, you see the kind of this cloud of points here. You might not know that there are actually 3 clusters, and it's only until you rotate. If you just plotted X and Y or something like that, it would look like this. But when you do the principal components analysis, you know, we start to recognize, okay, there is some clustering of our data here. Okay, and so that's kind of visually what is happening. We're looking for a rotation of our data so that the lower dimensional shadow that it casts resembles kind of the original structure of the data as closely as possible. And so when we say we want a lower dimensional representation or a lower dimensional projection that resembles the original data, one way to think about this is to say we want a projection that captures as much of the variance in the original data. All right? So we want to reduce the dimensionality of the data, but if we do that, we won't be able to capture all of the variance in the original data. That's just by nature. If you throw away one column of your data, you're losing information, right? You're going to be losing some information. So we're saying if I throw away a column of data, I want to kind of minimize the information I'm losing, right? And so the way we're going to minimize the amount of information that I'm losing is by maximizing the variation or maximizing the information that I have in the columns I do keep. Okay, so we're going to search for a lower dimensional projection that maximizes the variance in the resulting projected space. So when we do principal components analysis, we are effectively searching for how do we combine the values in our original data. We're looking for a linear combination of the original values so that the resulting values keep the maximum variation, right? So when you do SAT scores and you have a verbal component and a math component, your linear combination is just add the two together to get your total SAT score. So that's a very simple linear combination. But you know, for for something like, I don't know, the track and field, heptathlon or whatever, you know, how do you do this, right? You take, okay, you for the hurdles, you know, you completed it in 33 seconds. I have no idea what a hurdles time is, okay? You know, you completed this thing in 33 seconds, but then you jumped, I don't know, 6 meters. I have no idea what these track and field numbers are. I'm making stuff up, right? But, you know, how do you combine the 33 and the 6? You know, how do you do this, right? So you have to find, like, okay, we're going to multiply this by this, or, you know, in terms of running things, lower is better. So we probably want to invert the sign on that, okay? Whereas like jumping, like farther is better. So, you know, and then, you know, we have to kind of multiply them by stuff. And so what we're going to look for, you know, our original data exists in m dimensions, m being a big number, and we want to project it down to a lower number, d dimensions. And so we want to go from y, which exists in m dimensions, down to x, which has a length of d. So what we need to do is we are going to define a vector w, right? And we're going to have d of these w vectors, but w is going to basically be a vector of m weights. So we're going to have this w vector of weights, and we're going to multiply all the components in y by the vector of weights, and we're going to add them together. So we have this vector w, which is length m, and it gets multiplied by vector y, which is length m. So when you multiply these together, it's going to reduce to just one scalar value, right? When you do w transpose y, this gives us one scalar value. And so for the nth observation, we're going to multiply by w, and we're going to get x sub n. Now we have d of these w vectors. So if y exists in 3 dimensions, and I want to reduce it down to 2 dimensions, I'm going to have 2 w vectors. Okay, each vector in w is going to be length 3. So we're going to say, okay, we take x and we multiply by this, we take y, we multiply by this, we take z, we multiply by this, and that gives me basically x1. And then I do it again for the second w vector. We take x multiplied by this, or y multiply this, z multiply by this, we add them together, and we get our x2. So now we're going to have d of these w's. So, you know, if we're going from 3 to 2 dimensions, w, we have 2 different w vectors. Each w vector is length 3. And so we do w times y, and then we get that for each of our things. Okay, so what we want is we want to choose the values in w so that the variance in the projected space is maximized. That first vector, w1, will be the set of weights so that the variance in the projected value is as high as possible. And then the second vector, w2, will maximize the variance in x sub n2, but we have this condition that it must be orthogonal to w1. So that is when I do w1 transpose w2 is equal to 0. And this is a typo. This is wi transpose wj. Wi and wj are orthogonal for everything. So wi times wj is 0 for all I not equal to j. Okay. The third vector, w3, is going to maximize the variance in xn3, but must be orthogonal to all previous w vectors. And then to kind of avoid the problem of having infinitely many solutions, we're going to restrict the length of our w vector to be 1. Okay. Because if we were like maximize the thing, we can just make w huge, and it will make really big numbers. So we're going to say the length of w has to be 1. Okay, and to kind of make our math a little bit easier, what we're going to do is we are going to center the original data. So our y vector, we're going to subtract off the mean of y so that the mean of y will be 0. Okay, so we just kind of center our original data. So wherever y is, we just slide it down so that the mean of y is equal to 0. And that's going to really simplify the math that we have to do. Okay, And to kind of get us started, we're just going to work with one vector w, and we're going to say, okay, my data in y, for my nth observation in y, y exists in m dimensions, and we want to just reduce this down to one dimension. So we're going to just get the nth value x. So x of n is w times w transpose y. W transpose y sub n. This is going to give us the value, okay? And so what is the variance of this projected data? Well, it's going to be sigma x squared using, I guess, our biased variance. You know, xn minus x bar, quantity squared, divided by 1 over n. That's going to be our variance of our projected data here. And if that is the case, then the mean of x bar is we can show is going to be equal to 0, right? So the mean of x bar is the sum of xn divided by n, and we know x of n is the result of doing w transpose y sub n, and because w is not affected by n, it's the same for all n values, we can pull it out, and we're going to have w transpose times basically the mean of y sub n. We know the mean of y sub n is 0, so we've got w transpose times basically 0, so we know that the mean of x bar is going to be 0. Okay, what is our variance? So if we're going to say, okay, what is the variance of this thing? We have the variance is each x minus x bar. We know each x bar is 0. So we're going to get 1 over n times basically the sum of xn's squared. We know our xn's is w transpose y sub n. That's how we get that. And so if I square that, that's the equivalent of w transpose y sub n transpose w. And again, the y's are affected by our summation of n. We have different values of y for each subscript n, but the w's are the same for all of them. So I can pull the w's out of the summation. So overall, I have w transpose, the sum of yn transpose, times w. Yn times yn transpose is going to give me an m by m matrix, but that's okay. W transpose times this will reduce still to a scalar value, a 1 by 1 scalar value. And we want to maximize this thing. Okay. So one thing you'll note is that this, what is this? Yn transpose is equivalent to the covariance matrix. Because we know y bar, the mean of y is 0, right? So this is what I have. I got the sum of yn transpose. This is equivalent to saying I've got the sum of yn minus y bar transpose, right? So this is our definition of the covariance, and it simplifies to this because we set the mean of y equal to 0. So our variance of x can be simplified to say we've got w transpose covariance matrix times w. And we're trying to maximize this quantity. This is a scalar value. So we have a constraint, okay? We say we want to maximize this quantity. We want to maximize this variance, which is found by doing w transpose c times w, but we have the constraint that w transpose w has to equal 1. Otherwise, I could just make my w values like infinity, and that's going to make this thing a really big value. So we have this constraint that w has to have a length of 1, and so how do we maximize something subject to a constraint? We're going to use a Lagrange multiplier. So this is the quantity that we want to maximize, and we're going to subtract off lambda times basically our constraint that w transpose w minus 1 has to equal 0. So this is what we're going to do. And now I want to maximize this, so I'm going to take the derivative of this with respect to w, and I'm going to set it equal to 0. So when I take the derivative or the gradient of our quantity with respect to w, I'm going to get w transpose cw becomes 2cw, and then I have lambda w transpose w becomes negative 2 lambda w, right? That zeroes out. We're going to set this gradient equal to 0, and I'm going to solve for w. So I'm going to add 2 lambda w to both sides. And so now I have covariance matrix times w is equal to lambda times w. And does this look familiar? We have matrix times a vector is equal to scalar times a vector, right? So that is that's the setup for an eigenvalue, eigenvector type of thing, right? So w is going to be the eigenvector of C, and lambda is going to be the eigenvalues. So when we say we want to find this solution where we have matrix times a vector is equal to a scalar times a vector, the solution is that w is the eigenvector of C and lambda is the eigenvalue. And the eigenvalue eigenvector pair with the highest eigenvalue will be will result in the projection that produces the highest variance for W1. So that's going to be the solution there, okay? So the way we do principal components analysis to go from m dimensions down to d dimensions is we have to center the data, so the column means are all equal to 0, okay? You can optionally scale the data so everything has a variance of 1. If you do that, then the covariance of your scaled data is equal to the correlation matrix. So you can do principal components analysis on the correlation matrix as well. But basically, if you don't do that, you just kind of shift everything down so that the mean is 0. You compute the covariance matrix of your center data. You'll take the find the eigenvalues, eigenvectors of that thing, and then you'll select the eigenvector with the highest eigenvalues, and then your projected data is going to be x times y times w. So you have to become familiar or comfortable with finding eigenvectors of a 2x2 covariance matrix. Let me just go ahead and do a simple example here. If RStudio will start up for me. Okay, well, let me go ahead and give you your third view quiz answer. Last view quiz answer will be the letter B. B as in bear. B is our last view quiz answer. Okay. Something is not working with my RStudio. Okay. Well, as soon as I say quit, it seems to come back alive. Let's try this again. What's going on? Everything is empty. Okay, here we go. Okay, so let's take our y and we'll make a matrix. And in this matrix, let's put in some data. We'll put in 1, 1, 1, 2, I don't know, 2, 2, 3, 3. Let me just make a. Okay, and let's change things up here. So let's do 2, 4, 4, 3. I don't know. 5, 2, 6, 6. Okay. So we'll do that. We'll do by row equals true. No of columns equals 2. Okay, so this is my y matrix, and I'll go ahead and plot y1, y2. Maybe this isn't so great. Let's make this a little bit more extreme. Let's do 0, 6, 9. Okay, so here's our data, and we're going to try to find a rotation of this. Okay, so I'm going to centered y is going to be, let's do column means of y. This gives me the column means of y. So for y, I'm going to take y and subtract off the column means of y, and then I have to transpose that back. All right. Does that work? Center y looks like this. And what is column means center y? Okay, column means of centered y is 0. That's what we want. All right, so now we're going to get covariance of y. And I'll ask for the covariance of our centered y. So covariance of y gives me this 2 by 2 matrix. And now we'll call we'll ask eigen on covariance of y. And if we ask for what is the result of eigen, I get 2 eigenvalues and I get 2 eigenvectors. So what I'm going to do is I'm going to do PCA1, which will be my first eigenvector. So I'm going to call eigenvectors, and we will take our first column. So this is PCA1. And so now my x is going to be PCA1 times center y. Oops. Of course, I have to do y times w. So this is what our data looks like if I rotate them. Here, actually, let's call this x1, and let's do x2. So the second principal component will be take the centered y and multiply it by I've got PCA1, PCA2. And here, let me plot x1, x2, and this will be a rotation of our data that maximizes the variance here. So I don't know if we can see this. So I'm going to just kind of, so here's the original data, and when we rotate it, it looks like this. Okay, so can we kind of see that? So original data, and this is just a rotation that maximizes the variance here. Now, if I decide to throw away one of the variables, and I just say we're going to plot x1 and 0, basically we're going to lose all of the second dimension information here. So I'm going to just plot x1 with a bunch of zeros. Okay, so this is if I threw away x2, the data gets reduced to this. Okay, so we lose a lot of information, right? But overall, we're not losing too much. Okay, so if you did reduce the data, you could also kind of transform it back. Okay, and the transformed data, will have lost information. So if I just take x1 and I can transform it back by multiplying it by the transpose of PCA1, okay, and that will give me two-dimensional data, and I can plot this, and this is so here's the original data, we rotate it, we can reduce it down to one dimension, and I can rotate this back to recover our 2 dimensions, okay? And we can see, we've lost some information. You can kind of think of this as, if we could take people's SAT scores, right? And this is something, somebody who got like 800 on math and verbal, okay? Over here, if this is a math score and this is verbal score, this might be somebody who got like, I don't know, higher math, lower verbal. So maybe 700 math, 500 verbal, okay? Over here would be the opposite, high verbal, lower math. So maybe 700 verbal, 500 math. So 500 math, 700 verbal. So 700 math, 500 verbal, 500 math, 700 verbal, or something like that, okay? We can say, I just want to reduce it down to one dimension. Basically, we're going to say, just give me your composite, your total SAT score, okay? This person over here, 1600. These people, 700 math, 500 verbal, 500 math, 700 verbal basically appear the same. Their total score was 1200, okay? Now, we're going to try to rotate this back. What's happening here is we say, okay, try to guess what the math and verbal score was based on their composite. So, because we said we don't want both scores, we just reduced it down to 1. And so now we have, these 2 people that got 1200s total. And now we're trying to say, okay, if you had to guess what the original math and verbal scores were, you'd say, okay, well, my best guess is going to be like they split it evenly. So basically, both of these people, we'll just say we're going to, when we try to recreate the 2-dimensional data, that person who got 700 math, 500 verbal, we're going to say, we're guessing 600 math, 600 verbal. The person who got, what did I say? The other thing, 500 math, 700 verbal, or the other, 700 math, 500 verbal, whatever I said, we're also going to guess, because their overall score was 1200, we're guessing their composite, or their individual scores was 600, 600, after we reduced it down to one dimension, okay? So you lose information. Anytime you do dimension reduction, by definition, you're reducing the amount of information you have, you're losing information. This gives you a little bit more of the kind of clarity. This was high on component 1, lower on component 2. This one's lower on component 1, higher on part 2. We are just saying, it's too hard, so we're going to reduce it down to one dimension, and we can kind of get something back. But again, now those 2 individuals that were different kind of look the same here. And that's what dimension reduction does. So you might wonder, like, why do we want to do this? Well, dimension reduction, again, is helpful in that it's easier to think about a fewer set of numbers than a whole bunch of numbers, right? If you have high dimensional data, so this is extreme, where you're going from 2 down to 1. Our brains can usually keep track of 2 numbers in our head. But if you have like 70 numbers, that's really hard to think about. If you can reduce 70 numbers down to 3 or 4 numbers, it's a lot easier. You're going to lose information. That's the very nature of it. But you might be able to kind of, still preserve a lot of information despite the reduction in data. Okay. So yes, when you reduce it down to one dimension, all your data lines up in a single straight line. Okay, and you can kind of try to recreate the original 2-dimensional data. Again, if you had to guess what was somebody's math and verbal scores if their total SAT was 1200, probably your safest guess would be 600, 600 or something like that. But again, the original data might show that it was something like this, okay? So PCA takes the original data, rotates it, allows you to throw away one of the dimensions entirely, and basically says this is kind of your overall ranking of things. And in one dimension, if you say, well, I want to try to recreate my 2 values, you can, but you've kind of lost that nuance there. And that's kind of how PCA does it. This is going from 2 down to 1 dimension is maybe a little bit extreme. Probably we don't do it too often, but I would say it's fairly common to go from, say, like 60 variables or 20 variables down to maybe 10 or 5 variables, something. It helps reduce problems because we know in linear regression, when you have high covariance or high collinearity between variables, that increases the amount of kind of variation in your parameter estimates. And so PCA is one kind of method that can be employed to reduce the correlation, to decorrelate your variables, and then try to stabilize your estimates there. Okay, did I give you all three of your view quiz answers? Okay, then that will be it. We will go ahead and end here for today. Have a great weekend. Good luck as you begin to study for your final exam, and we'll just make Monday's lecture optional. Okay, maybe I'll even do it online. I don't know. Just stay posted. I'll let you know what the plans are for Monday. Okay, have a great rest of your day.